several modules, starting with the first one. We are mainly going to discuss about a very important area of probability and statistics known as stochastic processes. It's a very, very important area, particularly because it has a large number of applications in a wide variety of areas. A large number of systems in the physical world can be modeled very successfully as stochastic processes, and therefore that makes it convenient to analyze and even make predictions based on such models. So what is a stochastic process? Roughly speaking, you want to model a system which is evolving with time, but the evolution is random. That's roughly what is a description of the model for stochastic process. Of course, the actual technical nitty-gritties and the definitions, etc., would come later, but I'll postpone that, and instead, just to get things going, I'll start with one of the simplest kind of stochastic processes known as Markov chains. So the first few modules would discuss that, and the reason why I'm going to discuss this as a first topic without getting into formal definitions, etc., of stochastic processes is really entirely because of the fact that this is very simple, doesn't require any technicality whatsoever. All that you need to know are discrete random variables and some basic manipulations with conditional probabilities, etc., that everyone learns in undergraduate probability. So that's the reason why I'm going to talk about this topic called Markov chains, and the next few modules really are going to discuss about Markov chains. Coming to the first module, what we basically want to do is I start with an example, which is a very simple example, and then try to get some properties and make some observations about this particular example, and then that would give you the motivation for what is more generally known as Markov chains. As I said, we are going to start with a very simple example to illustrate the main idea. It's called coin tossing game, and all of you have seen it in some context or the other. So a coin is tossed repeatedly. At each toss, you either win or lose 1 rupee, depending on whether the toss results in a head or a tail. And of course, your net or accumulated fortune or capital fluctuates at each toss. We consider the following question. Suppose the game has gone on for some time, and you know how your net fortune has changed from the start till the time point, say the present time. I call it the present time. Given this information, what can you say about your possible net fortune after the next toss? Remember, you know the history up to that present time point. Well, let's denote for each toss the head probability to be theta, which is of course 1 minus the probability of tail. So what can you say? Well, clearly all you can say is, if your net capital at present is rupees X, then after the next toss, the net capital would be rupees X plus 1 or rupees X minus 1 with conditional, because remember, it's conditional on the entire history that you know. So conditional probabilities theta and 1 minus theta respectively. So the knowledge of what your net capitals had been at times prior to the present, even if you have it, does not matter, because your prediction is based on only what your present fortune is, that is X. This is called the Markov property. In evolving to the future, the process remembers only the present, forgets the past. So the present capital is X is all that matters. How you arrived at X, that present capital, is completely forgotten. So all the past values from the start till just before the present, even if given, are of no consequence whatsoever. Now, there is another, a little subtle but very, very important feature, and that is that the time period of the known past is also of no relevance whatsoever. That means whether your present time is after 50 tosses have been done or whether 5 tosses have been done doesn't make any difference. The transition from the present value to the possible future values follow the same rule irrespective of how much time has passed. This is a very, very important property. This property is called time homogeneity. So mathematically speaking, let's put the whole thing in mathematical language now. Denote x naught to be your initial capital, that means the capital that you started with, and for n greater than or equal to 1, let xn be your net capital after the nth toss. Of course, each xn is a random variable taking values in the set S, which is in this particular case Z, the set of all integers. That's a standard notation. If I look at the sequence xn for n greater than or equal to 0, it represents the fluctuation or evolution of your net fortune with successive tosses, and from what we have just now seen, they satisfy what is called time homogeneous Markov property, as already seen before, namely that for every n greater than or equal to 0 and for every x0, x1, xn minus 1, x and y in S, which in our case is set of integers, the conditional probability that xn plus 1 is y given the past, namely x0 equal to x0, capital Xn minus 1 equal to little xn minus 1, and capital Xn, that is the present fortune, equals x, that conditional probability is theta, 1 minus theta, and 0, according as whether y is x plus 1 or x minus 1, or y is neither x plus or minus 1. That's exactly, mathematically putting what we have just now observed. Now, it turns out that in a large number of situations involving random evolution with time, the same feature as observed in the coin tossing game holds. And this makes Markov chains one of the most important and widely used models for understanding and analyzing such systems. Like in the case of the coin tossing game, we would only consider systems whose possible values, they are often called states, at different points of time lie in a countable set. Recall that in the case of coin tossing game, the set of possible values were integers. So now I make a formal definition of what is called a Markov chain. Let S be a countable set, so that will be the set of possible values for the evolution. A sequence xn indexed by n greater than or equal to 0 of random variables taking values in S. Remember, S does not have to be a subset of real line, so we are not necessarily talking about random variables taking real values. So you have to get used to that. So such a sequence is said to be a Markov chain if this property holds. It's exactly what, or sort of similar to what we observed in case of a coin tossing game, namely that for every n greater than or equal to 0 and for every choice of x0, little x1, little xn minus 1, little x and y in S, the conditional probability on the left hand side, which is conditional probability of xn plus 1 equal to y, given the values of capital X0, capital X1, etc., all the way up to capital Xn equal to x, turns out to be same as simply the conditional probability that xn plus 1 equal to y given xn equal to x. So all this information in the conditioning that capital X0 was x0, etc., all the way up to capital Xn minus 1 is little xn minus 1 becomes completely relevant. And then comes, so this is a Markov property, then comes the time homogeneity, that is, this conditional probability doesn't depend on n either. So you could as well put n equal to 0. That means this is the same as the conditional probability as if given x0 equal to x, the conditional probability of x1 being equal to y. So it ultimately depends on only two things, the present state x and the future state that you're trying to predict, namely y. Nothing else it depends on. So it's proper to call this quantity pxy a function of x and y alone. Okay, so the definition that you have seen really captures two properties. One, the conditional probability on the left does not depend on, as we saw, little x0, little x1, etc. up to little xn minus 1. That's the first equality. And two, it does not depend on n either. That was the second equality. Thus, a Markov chain by definition satisfies both Markov property and time homogeneity, although the time homogeneity property is not reflected in the name. It's simply called Markov chain. The set S here is usually called the state space of the chain, and the elements of S are called states. The numbers pxy that we saw That is a conditional probability that xn plus 1 would be equal to y given xn equal to x, or which is the same as conditional probability that x1 would be x given x0 equal to y. These probabilities, as xy vary through the state space, are called transition probabilities of the chain. So what do they mean? They stand for the following. Given the history of the chain up to any time point n, Pxy represents the conditional probability that the chain will move from its given present state x to the state y at the next time point. So it's a probability of making a transition from the present state x to the state y at the next time point. Now, from the definition, these following properties are quite obvious. Since Pxy's are conditional probabilities, they have to be greater than or equal to 0 for every x and y s, non-negative. And of course, since Pxy for fixed x gives the conditional probability of xn plus 1 being taking the value y given xn equal to x, if you sum these things over y, the sum should be 1 because the conditional probabilities also should add up to 1. So these are two properties that transition probabilities satisfy. Now, before we get into any more of the theory based on the definition, it's time that we look at some examples. First example is a very, very simple example. It's called on-off chain. But nevertheless, it's extremely useful in many contexts. So imagine a system which can be in one of two states, on or off. Like it could be a machine, on or off. These are the two possible states. Now here's the model that we assume. If it is off at time n, then the chances are that it will be on at time n plus 1. That chance is alpha. Well, the chances of going from an on state to off is beta. And we assume that that is the case irrespective of past history. That's a Markov property. Denoting on and off states as states 1 and 0 respectively, we get the simplest of Markov chains with two states. I can write the state space as 0 and 1. These are just names for on and off. And transition probabilities are transition from 0 to 1 is alpha, off to on alpha. Of course, that has to be 1 minus P00, which is off to off. And probability of transition from on to off is beta, which also has, of course, has to be 1 minus the probability that if it's on, then it remains on. So that's one very, very simple example with only two states. Next, a very important example called random walk on integers. So suppose you have a sequence xi n indexed by n greater than or equal to 1. These are integer valued and IID random variables, and the common distribution is given by that probability that any xi n takes the value I is theta I for I in z. So these are integer valued. I define a sequence xn indexed by n greater than or equal to 0, again integer valued sequence of random variables, and they are defined like this. X0 is any integer valued random variable independent of the sequence in, and then the other xn's are defined like this. X1 is x0 plus xi1, x2 is x1 plus xi2, and so on. Xn is xn minus 1 plus xn. Of course, you can see that that is the same thing as saying xn is x0 plus xi1 plus etc. xn. So every xn is obtained by simply adding xn to the previous x, namely xn minus 1. We continue with random walk. One can easily see that xn is a Markov chain with state space, of course, integers, s is z, and the transition probabilities are easy to see that they are given by Pxy equal to theta y minus x. That's because Pxy is the probability that xn plus 1 would be y given xn equal to x. But remember, xn plus 1 is xn plus xi n plus 1. So probability of transition from x to y is the same as probability that xi n plus 1 takes the value y minus x. That's why Pxy is theta y minus x. So you just write the conditional probability definition in terms of these random variables and easily derive this. This is called the random walk on integers. You can physically think of it this way. A particle is moving along integers through random IID steps. So the steps of the particle, each individual step of the particle, they are successive steps are IID, random steps. They can also be called increments. And then xn is simply the position of the particle in the set of integers at time n. So of course the position at time n would be a sum of the increments plus the initial position, which is what the formula gave. Now if you go back to the coin tossing game that we started with, you can easily see that this is just a special case of this random walk and integers when the increments xi I take values plus or minus 1 only. That's all. So remember there, every time the coin is tossed, your increment is either plus 1 or minus 1, and they're independent. So coin tossing game that we saw is just a special case of this, and because of this simple nature of increments plus minus 1 only, it's called the simple random walk. Now an important property of this particular Markov chain, namely the random walk and integers, is that space homogeneity. That means if you look at pxy here in this particular example of random walk, pxy turns out to be, of course it's supposed to be always a function of x and y only, but in this particular case it depends on x and y only through y minus x. Now that may not be generally true for all Markov chains. So this is a special property of random walk on integers. So it's not a difficult exercise to show that random walks are the only Markov chains with this property. That means only Markov chains on integers whose transition probabilities satisfy the space homogeneity. You can easily show that. Our next example is renewal chain. Suppose that running of a process depends on an item that has a random lifetime. It could be a particular part of a machine or something. When that item breaks down, a new item is installed in its place at the start of the next day. We make the following assumption: lifetimes of successive replacements are IID, random variables, with common distribution given by, so L here is a generic notation for lifetime. So lifetime is I, probability of that is theta I. So lifetime can be I for I equal to 1, 2, 3, etc. with probability theta I. Now what is the xn that we are going to consider? So the next one. So let xn denote age of the item in use on day n for n equal to 0, 1, 2, etc., etc. So remember, so as the process goes on day n, the item that is in use may have been the first item that was installed. That could be because the first item never broke down until day n, or there could have been many replacements in between. So you don't know the item that is in use, whether it's a new item, when it was installed, etc., etc. So that's what we represent by xn. It's the age of the item which is on use on day n. It's not so difficult to see that xn is a Markov chain. State space is clearly natural numbers, 1, 2, 3, etc. because the age can be only 1, 2, 3, etc. 1 day, 2 days, etc. And the transition probabilities are interesting. Of course, if the age today on day n is of the item in use is x, then on the next day, n plus 1, there are two things that are possible. Either the same item would still be working on the next day, in which case age would become x plus 1, or the other possibility is the item that is in use today with age x may break down today, in which case on the next day it would be replaced by a new item whose age would be just 1. So if the age of the item in use today is x, then the transition on the next day are possible, only two possible values, either x plus 1 or 1. And the probabilities are given by these formulas, which depend on the distribution of the life. And for all other y's not equal to 1 or x plus 1, pxy is 0. Now to derive this formula for pxx plus 1 or px1 in terms of the conditional probabilities of L, you have to simply realize that xn equal to x, that is the item in use on day n has age x, really means that the item in use on day n has survived at least x days. That's exactly what it means. That means the life of that particular item which is on use on day n is greater than or equal to x. That's all you have to realize. Then the formula is pretty easy to derive. Okay, so here is our next example. It is called queuing chain because it models queuing systems. But of course, keep in mind that it's only a toy model to begin with. Later on, at some stage in a different module, we'll see a slightly more realistic model. But anyway, let's understand what this toy model is. First of all, there is a service counter and the customers arrive at the service counter and queue up for service. The modeling of the service is like this. If at the start of a period, no customers are waiting for service, there will be no service during that particular period. Okay? So, for any service to be given in a particular period, there has to be at least one customer waiting at the start of that period. Now, otherwise, that means if at the start of the period, there is at least one customer waiting, maybe more in queue, then only the first customer in queue is served during that period. So, only one customer served during any unit period. So, I mean, that's why we call it toy model. Now, what is random about this? The only thing that is random about this process is arrivals during successive periods. That means how many customers arrived during successive periods of time. So, let us assume that the arrivals during successive periods are independent with common distribution given by, so xi here represents the number of arrivals. So, probability that xi is I, that means there are I arrivals, that probability is theta I for I equal to 0, 1, 2, etc. So, there could be, it is possible to have no arrivals in a particular period at all, we allow that with probability theta 0. Now, what is it that we are interested in? Well, here is the quantity of interest. On day n, that is in the nth, at the start of the nth period, what is the length of the queue? We call it xn. So, this is the process that we are interested in, and it is clear that as n changes, this number also changes, evolves with time, and one can easily see again that by writing down the conditional probabilities, etc., that this xn is again a Markov chain. Now, the state space is z plus, which means all non-negative integers and transition probabilities given by this. If the size of the queue at the start of the nth period is given to be x, then what happens? If x is greater than or equal to 1, that means there is at least one person in the queue at the start of the nth period. Then you remember the model says that the first person in that queue would go for service. That means that person is out of the queue. So, it was x to begin with at the start of the day. One of them gets service and therefore out of the queue. So, at the start of the next day, in order to get to y as the length of the queue, y minus x minus 1 many new customers arriving on that particular day. And that probability is theta y minus x plus 1. Of course, remember this is for x greater than or equal to 1. The formula is slightly different if x is 0, because if x is 0, that means there are no customers at the start of day n, then there is no service. So, it remains 0. So, on the next day, in order to get the size of the queue to be y, there has to be exactly y many new arrivals on that day. So, that is why P0y is theta y. So, this is pretty simple. The next chain is a very important model in physics. It is called Ehrenfest diffusion chain, and it was historically a very, very significant model, even though very simple, in resolving debate, a long-standing debate in quantum physics. Anyway, we won't discuss about that. So, the model is very simple. Consider d many balls distributed between two boxes. You have two boxes, and the d balls are distributed in some fashion between two boxes. So, what happens is, out of the d balls, one is selected at random. So, you can think of it this way. Suppose the d balls are numbered 1, 2, 3, 4 up to d. You select one number out of these d numbers at random and select that particular ball. Then what happens? The selected ball is in one of the boxes. It is taken out of that box in which it is and then transferred to the other box. So, which means we change the distribution, and that happens in a random way because the selection is random. And then the same process is repeated. We do the same thing again and again and again. So, let xn denote the number of balls in box 1 after the nth turn. Again, you can see that Xn is a Markov chain. Its state space clearly would be, number of balls in box 1 could be 0 or 1 or at most D. So this is the state space. And the transition probabilities are like this. From a state X, you can either go to X minus 1. That happens if the ball that is selected comes from box 1, then that ball is taken out of box 1, and the probability that the ball selected is from box 1 would be X over D, given that there are X many balls in box 1 at present. So the probability that one of them is the one that is selected is X over D, because each ball, remember, has probability 1 over D of being selected. And by the same kind of argument, Pxx plus 1 is 1 minus X minus D, and of course from X transition to only X minus 1 or X plus 1 is possible. And that's what it says, Pxy is 0 for y not equal to X minus 1 or X plus 1. As I said, this is a very important model in physics. It captures an essential feature of diffusion of particles. For example, whenever a box carries a very large share of the balls, so let's say X is pretty close to D, the chances of a ball moving out of it into the other box are very high. For example, if X is pretty close to D, then Px x minus 1 is almost 1. So in this module, what we have basically done is we started with a coin tossing game, which is essentially repeated tosses of a coin, where every time you win or lose a rupee, depending on whether the coin results in a head or a tail. And then we saw that if you look at the net fortune, net capital after successive tosses, then they follow an interesting property. And taking a cue from there, we defined what is called a time homogeneous Markov chain. We defined, made the definition of transition probabilities. And then as a beginning, what we did was we looked at several examples of such Markov chains, both with state space a finite set or state space infinite. So next thing would be to go back to the theory and look at some basic properties.